In this video, I will introduce you to probability distributions. The binomial distribution is a useful way to get a feeling for what these types of distributions tell us. They're incredibly important in statistics, and we'll be working with probability distributions for the entire semester. Okay, so we'll start with something really easy. All right. So let's say you have a coin that you want to flip two times. Okay, so what could happen? Well, you could get heads both times, right? You could get a head on one of the flips, but not on the other flip. And you could get tails both times, I suppose. So what is the likelihood of these various events? Well, you may be able to figure out just using simple probability that you're more likely to get just one head and one tail than you are to get two heads or two tails. And that's because there's two different ways to get a single head, right? You could get a head on the first flip, or you could get a head on the second flip. Whereas to get two heads, you would have to get heads on both flips. All right. So that sort of thing you can solve just usually using simple fractions and things like that. But probability distributions a lot of times are easier for visualizing these sorts of things. So what we're looking at here, this is Lane's binomial calculator. All right, let me just go back and show you how to find it. All right, so when you open the home page of Lane, remember go to version 2, and there's this list of table of contents. You can go down and click on calculators, and you'll find a variety of different calculators. And we're going to look at the binomial distribution. Okay, so that's the default screen. What you put in here, this is the number of trials. So if I flip the coin twice, that's two trials. So I'm going to change that to 2. And then what we have here, pi, this is the probability of success. So with a coin, there's only two things that can happen, heads or tails, right? You have to decide which of those you want to be a success. We'll say getting heads is a success. So there's a 50-50 chance of getting heads, right? So that means that the probability is 50% getting heads, which is 0.5. Okay, so that's why I have 0.5 listed here for pi. All right, so what this shows us is this is the probability distribution. Now let's see what it's telling us here. As you can see at the bottom, these are the number of times we get a success. So here's this bar here represents getting two heads. And if you read over here on the y-axis, these are probabilities. See that? It's labeled probability. So what this means is there's a 25% probability of getting two successes, two heads. All right, so that's the same as 1/4. On the other hand, there's a 50% probability of getting only one head. And we were just talking about why that is, because there's two different ways to get a single head. You could get it on the first trial or the second trial. And then there's a 25% probability that you'll get two tails, so no heads at all. Now, notice if you add these three probabilities up, you get 100%. And all the various probability distributions, the areas underneath the distributions or that make up the distributions, usually there's a curve of some sort, but the area of the distribution is equal to 100%. Okay, so what if we wanted to do something a little more complicated? Like instead of just flipping these coins twice, what if I wanted to flip the coins, I don't know, let's say 10 times? Then what's going to happen? Well, if I wanted to know how likely am I to get 3 heads and 10 flips. We can use the binomial distribution to find that out. That also can be done with a bunch of fractions, but it starts getting really, really complicated mathematically. Now, there's a formula that will give you probabilities, a binomial formula, but usually, well, let me just put it this way. In this class, we are going to use this calculator just because it's easier for one. If you use the formula, sometimes you'll get a slightly different answer. This is due to a rounding error. So I ask that in this class, you always use this calculator. Okay, so let's see what this is telling us here. So, like I said, what is the probability of getting 3 heads? Well, it's the area of this little bar right there. Now, you can kind of look over here and see it's about 12%, but we can actually, what this is a calculator, and it's going to tell us exactly what that area is. So to get just the probability of getting 3 heads, what we would do is we would select this button here between, and you enter a 3 and a 3 at the other end because it's inclusive. You see that? Now if you look at the graph, you'll notice that just the 3 is shaded in. Here's the probability. So in this class, we always report answers rounded off to 3 decimals. So we would be dropping the 2 here. The answer would be 0.117. Okay? Remember, you don't always drop when rounding. You don't just drop the last digit. If this is a 5 or more, then that number will go up. Otherwise, it stays the same. So if this had been 0.1175, then I would say the probability is 0.118. Okay? All right, now let's see. Another thing that we do a lot of times is we try and figure out what is the likelihood of getting a value, you know, that is a certain score or lower. So for example, if we wanted to know how likely is it that we will get fewer than 4 heads, for example. Well, then you would select below here, and you have to put in below 4, you see. So notice that the 4 is shaded blue, but the 3, the 2, and the 1, and the 0, can't even see the 0 hardly, it's so small, are all shaded red. And then you hit recalculate. Notice the probability of getting a 3 or fewer is 0.1719. Okay. Now, another type of scenario we do a lot of when we're working with statistics is we ask, well, how likely is an extreme value? Okay, so you can sort of think of 3 as being an extremely low number, right? That's a low number of heads. The most likely thing that's going to happen is we're going to get 5 heads. See how the 5 is exactly in the middle? Wonder what that is. Notice that is the number of trials times the probability is what, and that's always the mean of the binomial distribution. So if you want to know what the mean of the binomial distribution is, it's pi times n. Okay. All right. So this is an extreme value, right? How extreme is it? Well, it's not that extreme. I guess it's 2 points below, right? So the extreme value on the other end would be 7. This would be 2 above. So since this is symmetrical, you could almost just multiply this by 2. But binomial distributions are not always symmetrical. So the best thing to do would be to find first what is that area, right? And then add it to the area on the other end. So we would need above, I guess, 6 to get the other end, all right? So if we wanted to know the probability of getting extreme scores, like really low scores and really high scores, we would need to add those two. Now, this can be important when you're working with probabilities that are different from zero point 0.5. Look what happens when we change the probability to zero point 0.2. So like, let's say we had a coin that was a little screwy and it only came up with heads 20% of the time. Then notice that, the shape of the binomial distribution is quite different. Part of the reason is it's just scrunched up this way. You can't have less than 0 as an answer. On the other hand, if you're flipping it 10 times, you could conceivably get 10 heads. It's just the probability of that is really low, which is why we can't even see it here. And I'm just curious, let's see what happens if we put above 9, so just 10. Notice this says probability 0. It's actually not 0. It has been rounded off to 4 decimals. So what this is, the probability of getting 10 is less than 0.0000. Or if you're rounding off to 3 decimal points, we would just say the probability is 0.000. Okay? So that's how we can, that's how we handle probabilities that say 0 here. All right, so if you're rounding off, you'll actually put 3 zeros as the answer. Okay, now let's see what else we want to take a look at. There are other, so one thing I really like about Lane's book is that we have these nice little visual aids that allow us to see what's going on when we're using these probability calculators. Now, unfortunately, not all of his calculators give us visual aids. So we have one for the binomial distribution, and we also have one for something called the normal distribution. So most students are familiar with normal distributions. We're going to actually be looking at these more closely in Chapter 7, which is what the next unit is going to cover. So it doesn't hurt to meet this distribution now. With the binomial distribution, we're usually dealing with something like counts. It's almost always discrete data of some sort. Normal distributions, well, they can work with discrete data and also continuous data. So they're sort of a different, they're for a different use, as we'll see. So here's a good example of what a normal distribution might be used for. Let's say, in this area we have these butterflies that have, oh, I don't know, a mean width of like 50 millimeters, we'll say. All right. And then let's say they have a standard deviation of 10 millimeters. So there's a lot of variation in the size of these things. Now, what we have in this probability distribution, remember the area of this is 100%. So what this means is, think of this as like a model. This is a model of all the butterflies on the planet, or in the universe even, or that have ever existed of that species, that has the mean of 50 and the standard deviation of 10. So among all those butterflies that have ever existed, yeah, some are kind of small and some are really, really big, but there aren't very many of those. Most of them are clustered around this average width, okay? So you might be asking, well, let's see, what could we do with this? So something that a biologist might do if we had a year where it rained a whole lot and, for some reason the butterflies are suddenly like really big in our neighborhood and we're kind of curious, well, maybe something has happened. And we just go out and we catch this butterfly and it's like, I don't know, 65 millimeters. So it's like over here somewhere. What if we wanted to know, well, how likely is it that we could get a butterfly that's 65 millimeters? Well, you would put above, and then you would put 65 here. All right. See how the area to the right of that is shaded? And here's the probability, 0.067. 7 would be how we would round that off. So it's pretty unlikely. That means there's about a 7% chance of catching this butterfly. And that is assuming that nothing has changed. Because remember what this is a model of. This is a model of this butterfly or of this species of butterfly when they're kind of like doing what they normally do. So if, yeah, it really has affected the butterflies, well, you would think that the mean might have shifted or something like that. All we can really do is take a look at this one butterfly and say, well, how likely is it, assuming that nothing has changed? So that's what that probability is telling us. So if we wanted to find an extreme value, okay, how would we do that? Kind of like before. So maybe, how likely is it just by chance we go out there and we catch a butterfly? How likely is it that we're going to get a butterfly that is like really big or really small? In other words, what's the likelihood of these things? Well, again, since a normal distribution is symmetrical, you could just double that to find the other side. But there's another way to do it that's sometimes easier. We could just use a calculator like this to tell us this. So you can click this outside here, and then you put 65 here, all right? And now we wanted, I guess that's 15 below, so on the other end, that would be, I guess, 35, right? Okay. Okay, now notice how both ends of this distribution are shaded. So 15% or about 13%, that's the likelihood of just by chance going out and catching some really, really weird butterfly. One thing that tells me, if you think about it, let's say I'm kind of suspicious that maybe something has happened and the butterflies are bigger. So I go out and catch a butterfly and I measure it and it's 65 millimeters. Well, there's like a 13% chance that I'm going to get either a really big or really small butterfly. Maybe I would be jumping to conclusions if I said, hey, it seems to have rained a lot and the butterflies are a different size. In other words, we're going to get to something called hypothesis testing. And this is one of the things you do in hypothesis testing. You take new data and you see how it matches a probability distribution that you've generated. Okay, so it might be, I think it would be a bad move to say, well, it looks like these butterflies have changed because it's pretty likely that we would get a weird one. Of course, we usually work with samples, but for those, we have to work with a slightly different distribution. Okay, so we'll be talking about that more soon. All right, well, how about some of the other distributions we use? So, like I said, the binomial distribution and the normal distribution, these are distributions that Lane allows us to visualize because he's made these nice little calculators so we can sort of see what we're modeling. Remember what they are? They're models of kind of the universe. So this is a model of all the butterflies with means of 50 and standard deviations of 10. That's what this is. All the butterflies that have ever existed. Before, when we were looking at our binomial distribution, this is a model of what happens with flipping a coin if we flip it 12 times. This is how often heads are going to come up. That holds forever and ever. So that's what a probability distribution is. What's the likelihood of getting these values? Same thing with the normal distribution. What's the likelihood of getting a butterfly that's like over here? That's what this thing tells us. So there are other types of distributions. One you're going to be meeting in this chapter is the Poisson distribution. So these things have really weird shapes when you don't have a lot of trials and or probabilities of success, but then their shapes change to become more normal depending on what your probabilities of success are. And then this is something called a t-distribution. It looks a lot like a normal distribution, and we use it to interpret, similar things. Like notice we've got the two ends shaded, so we're kind of looking at an extreme value in this illustration. Unlike a normal distribution, it's a little more pointy at the top. A normal distribution would be a little more rounded. This is called leptokurtic when it's pointed like that. And then yet another distribution we use is something called the chi-square distribution. But all these probability distributions, they all work the same way. Think of them as models. Frequently, they're models of something called a null hypothesis. If they're not a model of a null hypothesis, they're a model of the universe, the way things are. And then to figure out how likely various events are, we just sort of find those events underneath the curve and look at areas, because the area under the whole thing is 100%, and that's the case with every one of these different distributions. Okay, so I hope this makes probability distributions a little less scary for you. And with that, we will end this video.